So from this point on, what I'm going to cover is first how to calculate the pH of a buffer solution, then I'll show you how that pH resist changes as we disturb that solution, then finally I'll cover why the buffer is able to resist those changes upon disturbance. But first, let's just learn how to calculate the pH. I'm going to start by showing you the long correct way, and then I'll show you a shortcut. And that's what we're going to write down, because the long correct way doesn't actually involve anything really new. So here's our example. What is the pH of a 0.40 liter buffer solution consisting of 0.180 molar formic acid and 0.200 molar of its conjugate base, the formate ion? So in this solution, we're taking both the acid and its conjugate and mixing them together. Notice these concentrations are within a factor of 10 of each other. And so this meets our requirements for a buffer solution that we wrote down in the previous video's definition. Now the long way to do this is to calculate the pH like we would a normal weak acid. Set up an ice table and then solve for x. There's only one little twist, but it's so small that for the most part we can do this exactly the same as before, hence it's going on the slides. So the one twist is that our product conjugate base is not at 0 like in previous problems, because we're starting with that initial 0.200. But from there everything goes the way that we've seen before. We would address the change, minus x, plus x, plus x. The equilibrium concentrations are just those initial values with these minus and plus x terms. We then take those values and plug them into a K expression. Now here's where having that initial concentration of product has an effect on things. Because when we apply the small x approximation, the following happens. We not only neglect this minus x term in the denominator, but we neglect this plus x term in the numerator. And that's because we never said that the small x only works on the bottom of the fraction. We just said that we can ignore plus or minus x terms if the K value is at least 1,000 times greater than the initial concentration of a species. Doesn't matter if the species is a reactant going down by x or a product going up by x. This is at least 1,000 times smaller than this initial concentration. And so we ignore the plus x up here just as surely as we ignore the minus x down here. This actually makes the math even simpler because now all we have is this one x over here. There's no squared term. And then we just solve for it with algebra. We get our x value is 1.6 times 10 to the minus 4. Do the small x check like before. Checks out, negative log that value, and we get our pH 3.79. So almost the exact same type of problem as what we did last lecture. Now we have a simpler and faster method for finding the pH of a buffer, and it's by using an equation called the Henderson-Hasselbalch equation. And the book goes into the derivation of this equation and how it relates to these K expressions we've been solving. I'm happy to show it to you as well during office hours, but in class I'll just write it down because you don't need to know its derivation, you just need to know how to use it. But if you're interested, please let me know. The Henderson-Hasselbalch equation, or HH for short, HHEQ, says that the pH of a buffer solution is equal to the pKa for the acid component of that buffer solution, plus the log of a ratio between the concentration of base in that buffer to the concentration of acid in that buffer. And we use initial concentrations, which is a definite estimate. What this is assuming is that the initial concentrations of base and acid don't effectively change once the two mix together and reach an equilibrium. In other words, our equilibrium concentration is equal to the initial concentration, which means that we are assuming that the small x approximation works, which we can pretty much always do for a buffer. So let's write some notes down. In parentheses, we will say, assumes small x works. In other words, we're assuming that the equilibrium concentration is roughly equal to the initial concentration, which we can do for a buffer. And you can verify that by looking at the previous slide where I showed the plus x term to the conjugate base and the minus x term to the acid were both small xable, and our final concentrations were effectively unchanged. And I will make one more note and stress that when we say base and acid, we are talking about the conjugate pair that makes the buffer. I'll show you why this is an important distinction when it becomes relevant in a future problem. We'll make one final point before seeing this equation in action, which is that if we have a solution where these two concentrations are equal, well then this ratio will equal 1, the log of 1 is in turn 0, and pH of that solution will just be equal to the pKa. That'll be an important point for later as well, but for now we'll just make a note. When concentration acid equals concentration base, the pH will equal the pKa. So let's put this equation to work. I'm going to do the exact same example that we did with the ice table and all of that, but this time I'm going to go through these two simple steps and use the Henderson Hasselbalch to figure out the pH. And this time I'll write it out since we're using a new concept. So step 1, if needed, do your groundwork. Figure out the pKa, the initial concentrations of acid and base. Those are given to us. Our initial concentration of acids, 0.180, conjugate base, 0.200. We don't have the pKa, but we do have the Ka, and the pKa is easily found from that number. So let's just quickly do that. Step 1, pKa is equal to negative log 1.8 times 10 to the minus 4. Solve, and we get 3, not significant because it's to the left of the decimal, 0.742 sig figs. Now we have everything we need. On to step 2, which is just plug everything into the Henderson-Hasselbalch equation. pH is equal to pKa, which we just found is 3.74, plus log. Our ratio of base to acid is 0.200 to 0.180. Plug it all in, and we get a pH of 3.79, which is in total agreement with what we got when we did the whole ice table approach. But notice how much quicker and simpler this is. And we'll make one final note, which is that we're going to assume that the small x always works for a buffer. No need to prove. Assume small x always works for a buffer. No need to prove it. No need to prove it. So unlike previous problems where I showed the small x check, here we won't bother because it's a buffer. Our next step is to see how that pH resists change upon neutralization. But before we do that, just to break up the monotony, there is a clicker that reaches back into concepts from last lecture. But we will of course do this clicker during Zoom.